today, we'll just be going through the basic definitions of time series. So this is how a time series dataset might look like. So most of the time, it'll be given to us in the form of CSV file, so we can load it using pandas. And in this case, I'm showing it as a 2D array. So there are several types of columns. So I will go through some from the last one, actually. So instances here actually means that, for example, if we're talking about time series at a grocery store, then instances can be different products that we have at the grocery store. Or if you want to bring it to a granularity of an entire store, then instances can be different stores at different locations. And then for each instance, there's a corresponding index. So in this case, it'll be the days, assuming this is daily data. So the days will go from 1, 2, 3, 4, 5, 6, and so on. And for each instance and each day, you'll have some type of features. So in this case, I'm showing n features. The first feature here is an example of a numerical feature. So it'll be just like a float number. The second will be a categorical feature. So it can be different classes that we might have, different types that we might have. And last example I'm giving here are called time covariates. So this will correspond to some time-dependent information. For example, what's the day of the week, whether it's a Tuesday, Wednesday, or Thursday, or it can be also hour of the day, day of the month, etc. So if we want to do time series forecasting, the idea is normally given maybe the last 30 steps and want to predict into the future for around maybe 10 steps. So the last 30 steps will be called context. So this will be a given information. And the next 10 steps will be called the forecast horizon, which we often use the letter tau to represent its length. So this, the first part is given, the second part is target. So in the context, you'll just get 1 point as a ground truth for every time step. And in the forecast horizon, in addition to just point forecast, which you predict the one value for every time step, you can also maybe predict a confidence interval as well. And we'll be talking about those in the next few lectures. So assuming our target, so intuitively, the target should only be known in the context. So that's part of the observed inputs. And in addition to just the target variable, for example, in this case, we also have some other type of numerical features or categorical features that we can use to help our predictions. So they can either be only available in the context, or they can also be available in the forecast horizon as well. So that will correspond to the observed inputs or no inputs. And there are also some static variables. So in this case, the instance ID will definitely be a static variable. So static means that it doesn't change over time. But for observed inputs and no inputs, they're both time dependent. And also a good example of no input will be the time covariates. So day of the week or some known holiday effects. So if you know that in 5 days we'll have a Black Friday. So you can also have the model take that in as no input. Yeah, so any of those can either be numerical or categorical features. So this is the same data frame that we had before on last slide. And suppose that the task is to predict 10 days given 30 days. So the first thing that we're going to do is we're first going to group the entire data frame by the instance ID, so the ID column here. So we'll take the IDs that equals to 1 and have it in one 2D array, and then all the IDs that correspond to 2 in a different 2D array, etc. So for each ID, we'll do the train test split. So in this case, I'm supposing that the entire data set has 1,000 days. So each ID has maybe 1,000 times n, which is number of features. So the train will be 70%. Just an arbitrary number I'm throwing here. So in this case, train is 70%, which we use day 1 to 700 as train split. And then validation will be 700 to 800, except that we don't really start at 700 because we're given 30 days as context. So in this case, our window for the validation set actually starts at 700 minus 30. So it's 770, 670, because we'll use the first 30 days as a context. And then we calculate the loss using a validation set. And same thing for a test. So we don't start at day 800. We need to feed in the first 30 days, which overlaps with the validation set. So if you're confused by anything, you can just unmute and ask right ahead. So once we get the 2D array for each that correspond to each instance ID, then we can divide it into rolling windows. So in this case, the way I'm doing it is I have something called a stride size, which is the number of non-overlapping steps between every 2 windows. So the first window will start from day 1, go all the way to day 40. And the second window will be starting from day 6. So I'm moving five days ahead. So going from day 6 to day 45. So for each one of those window, we'll be doing this task of given 30 days and predict the last 10 days. So this is one way of doing it. If we just have a defined stride size and we sample the windows this way using rolling windows. And alternative is to just choose the stride size to be 1. So I'm just enumerating all the possible positions for the window to start at. And then from there, I subsample n total windows to do the training. And of course, for validation and tests, you probably want to use the entire validation set or the entire test set. Yeah, and the idea of having this validation set is because we want to use it to calculate the loss on the validation set so that we can find the best stopping point, and we can also define the best set of hyperparameters. So either learning rate or number of layers, etc. So the third section will be on how we convert this rolling windows that we defined into something that we can feed into the neural network. So for the categorical features, we'll be doing one-hot encoding. What it means is that, for example, if we have a total of 5 classes, then class 0 becomes 1, 0, 0, 0. So the overall idea is you just have a bunch of zeros, which is the same number as the number of classes that you have. And you put a number 1 as the places where the class number equals that index. So class 3 will be, you'll be putting a 1 at index 3. And for the all numerical features, there are some models that don't require normalization, but for neural networks, it will definitely need to normalize them. So how you normalize them is oftentimes you just calculate its mean and standard deviation. So you subtract the mean and divide by a standard deviation. Or there are some alternatives in time series. For example, you can calculate the mean and just use the mean instead of the standard deviation to divide the data. And there are different ways of how you want to be calculating the mean and standard deviation. So you can either calculate the mean and standard deviation based on just a train split, or you can, for each instance, you can calculate the mean and standard deviation. So idea behind this one is, for example, if you are at a grocery store, maybe some products are very popular. They sell much better than some of the other products. Then you probably don't want to calculate the mean across all the products. You probably want to calculate a separate mean for the products that are very popular and a different mean for the products that are not as popular. And the last method of doing this normalization is given each window, we'll be calculating the mean and standard deviation based on this context. So the first half or the first 30 days, if you're talking about our example from last slide, and we'll apply it to the entire 40 days. So apply it to both the context and the forecast horizon. So empirically, most people are actually using the last method because if you have some kind of trend in the data set, then doing this window-wise normalization, after you do this window-wise normalization, it can kind of get rid of the trend and makes the input numbers follow a similar distribution as in the train set. And if you're dealing with some heavy tail features, maybe you want to do a log transform, or there are some other things you can do. For example, you can calculate the quantiles, etc. And it's always very important to remember to rescale back to your predictions for target variables. So when you input the numbers into your neural network, you subtract the mean and divide by standard deviation, then you should, for the output of your neural network, you should multiply back the standard deviation and then add back the mean to get the real scaled predictions. So this is like a bug a lot of people make. Yeah, so back to this example that we had from before. So the first thing we do is for all the categorical features, we'll do one-hot encoding. And then we also normalize numerical features. And then we take this middle part, so the n features that we have, as well as the instance ID. So in this case, there are 3 classes. So take this whole, each row into a long vector. So we'll be concatenating the entire first row here. So this will be the vector that we input into the neural network for day 1. And second row will be the vector for day 2, etc. Yeah, and the shape of the window will be t plus tau, which is how many steps we want to predict into the future, as well as just the number of features that we have. So let's get a overview of the entire training pipeline. So for each instance, we use rolling windows to to generate a bunch of rolling windows. We'll put all those windows from different instances together, and then we'll subsample a batch size number of random windows. And then for each window, we'll be predicting the next 10 days given the past 30 days. So for each target variable, we'll have its predictions as well as the ground truth. So when this process is called forward propagation, so we'll feeding data into the neural network and will generate a prediction for us. So maybe we can define a loss function. We can just use MAE, which is a simple loss function in this case, and we'll calculate the loss based on this function. So why we want to do a sample of batch size number of windows instead of just calculating the loss on a single sample, because a single sample can be very noisy, and the loss returned might not be a good indicator of the actual performance. So we actually need to average the loss across many windows, and the number of windows that we use is called batch size. So the forward propagation computes the model output, and the back propagation will update the model weights using the gradients that we calculate from this loss. Yeah, so in other words, we'll be just using this loss function, the loss that we calculated as a signal to update our weights in the neural network. Okay, and this is the first part that I plan to cover, and the second part will be on PyTorch. If you have any questions, it might be a good time to ask. So let's go back to the introduction of PyTorch. So the first thing I'm gonna talk about is, suppose you already have the model defined, then you can set it to train if you want to build a computation graph and you want to do gradient descent. So you are still in the process of training the model. And once you're done with training, and then you're evaluating the model, the good practice is to call model.eval and also wrap the evaluation code with torch.noGradient. So if you do this, then the PyTorch knows that you will not be requiring a computation graph and will be much faster and more memory efficient. And for training, we can think of it of having 5 steps. So you can have the model.forward. In this case, you probably want to input some parameters here. So maybe you can call it X. So maybe it will be the first 30 days that we talk about, and the predictions will be for the next 10 days. So model.forward, and you input X. And the shortcut is, instead of calling this model.forward, you can just call model parentheses directly, which is a shorthand notation for this .forward. So if we're dealing with the univariate case. So if our data set only has one variable, and our task is given the last 120 days, we want to predict the next 48 days. So in that case, the shape of our the tensors will be batch size times 120 times 1 for x. And for prediction, it will be batch size times 48 times 1. So given this, after you have this prediction, you can calculate the loss. So it'll be a loss function that takes in both the predictions and labels. So maybe this loss function can just be a MAE that we talked about earlier. And the shape of both the prediction and labels should be batch size times 48 times 1. And the loss should be a single scalar. So it should be like a numerical number. And you call it backward on the loss. So what you do is loss dot backward. So it is meant to do the backpropagation. And once you call this, it will use the computation graph that it built during this model.forward and this loss function here. So we use this computation graph to compute the gradients of the loss with respect to every weight in your neural network. So every weight in your model class. And then using this gradient, you'll be calling optimizer.step, which will update the weights according to that gradient I calculated. So suppose the original weight is W. So what you will do is you have W minus step size times the gradient of W with respect to the loss. So when you call this loss dot backward, it will actually store the gradients in this optimizer. And then last step will be to clean up those weights, those gradients from the optimizer to make it ready for the next iteration of training. So you won't be calling this optimizer.0 gradient. And next, we'll talk about what's going on inside the model class. So model will be an instance of net. So it seems like most of us has a background in computer science. So in this case, it's like you have a person, and then the person is the student is actually what I'm going to say is that the model is an instance of the net class. And then this actually corresponds to the next line here. So in this case, you want to inherit students from the person class. Yeah, I think this is actually an example that I had from last year. Let me actually delete this one so I don't get people confused. Okay, so anyway, so this net class you will want to inherit from the torch.and.module class. And then in the definite, so whenever you're defining a class, you want to have this definite. In this case, we'll define it to have two layers. The first layer is, let me come out the second half. So the first layer will be going from 100 to 50, and the second layer will be going from 50 to 30. And to also define loss function I want to use, which will be the MSE. So suppose this seems to be a bad example. Let me actually. Let me actually just get rid of the number of variables for now. Or we can just use one here. So suppose say our task is still to, given the past 120 days, I want to predict 48 days ahead, and we only have one target variable. So in this case, we'll be feeding to the dense layer number 1 first. And what you want to make sure is that the last dimension of your input tensor should match the first parameter here. So in this case, it should match the 100. Why do I have 120 here? Okay, let's change the numbers a little bit. So you'll do this, and by calling this 0 here, you'll be removing a loss index. And then after the first layer, you'll get, let me write it out. So after layer 1, you will get batch size. And then the first layer goes from 100 to 50. So we'll have batch size 50. Then then we feed into the second layer, which will go from 50 to 30. So after this layer 2, we get batch size 30. And maybe at the end, we might want to add the last dimension back. So we still have the batch size times 30 times 1. So the other way to think of it is that if we're just using linear layers, then the first parameter of your first layer should match the shape of your input tensor for the last dimension. And then the second parameter of the previous layer should match the first parameter of the next layer, if that makes sense. Okay, and then you can define two functions. So you can define a do train, which is when you want to compute the computation graph, and also calculate the loss. So be feeding this in, and it will return a single floating number as a loss. And you can also define a function for test, which is just doing the forward propagation and without calculating this loss. And next section, we'll talk about how we define data set, which is how we feed the data into the actual model. So you'll be inheriting from the dataset class, which is also you can get its full path from PyTorch. So be defining the train data sets right here. So assuming that we already get a self.x, which correspond to a bunch of, so this self.x, x has shape. So if we're working with neural networks, it's always very important to keep track of what's the current shape for all the arrays and tensors. So in this case, it'll be number of windows times context length times non-features, non-variables. And labels shape will be num-windows times your prediction length, which will be tau, and then also the number of variables. So assuming, in this case, we're assuming that we only have the target variables as input. And for the dataset class, you also have to define what's the total number of samples you have. So it will define it using this function, def underscore length. So this tells the model, tells PyTorch how many samples you have in each epoch. So if you call this data set and define a data loader, which we'll talk about later, it will just go through, iterate through every single sample in your available train set. So the last function that's important for the train data sets that you must have is get item class. So given an index, it will retrieve the corresponding sample. So in this case, we'll be extracting a sample from this first dimension here. So one window from this number of windows. And then based on this data set, you should feed this data set into another data loader class, which you can also get it from PyTorch. And what PyTorch do is that if you have a batch size defined, then it will call this get item function for batch size number of times. So retrieving batch size number of samples every time to train your network. Yeah, and given this batch size, we can feed into the actual model. So it can enumerate or loop through this train loaders that we define. So it'll be getting this train X and also the labels. So the last part is an overview of the entire process. So first you'll initialize the model, and then you'll define your train set, your test set. And for the train set, you will define a corresponding train loader. So what's important here is this batch size and also how you want to sample this index here. Do you want to sample them in ascending order, or you want to sample them randomly? So for train loader, most of the time people just use a random sampler. So randomly subsample batch size and number of windows. And for a test loader, it's the same thing, except that maybe you don't want to do this random sampler. You want to process things in the original order. And you want to define an optimizer, which is how you want to do this gradient descent here. So this is the most simple form of gradient descent. There are also more advanced methods. So this optimizer is used to define which kind of gradient descent I want to use. So to define the scope of which parameters that the optimizer should keep track of. So in this case, I'm only limiting its scope to the other parameters inside the model. And also have this learning rate. So what's the step size I want to do the gradient descent. So first, when we're doing the training, we want to call model.train, and then we for loop through the train loader. So this will train the model for one epoch. So maybe in addition to one epoch, you can keep it trained for multiple epochs. That's fine as well. So for each epoch, for each iteration in the epoch, you first want to clear out the gradients in your optimizer. Then you do a forward propagation to calculate the loss dot backward to calculate the gradient using this loss, and then use the optimizer to update the model parameters using this gradient. And once you are done with training, you can call model.eval and then have torch.noGradient, then for loop through your test loader to get your final prediction for every sample in your test set.